Howdy! This is your friendly neighborhood physics teacher here, and I'm here to go over your waves and optics review. Now, the first few pages of your review is just really good information. It breaks down the different types of waves, sound, light. It breaks down the different types of ray diagrams going from mirrors to lenses and concave and convex. It gives you all kinds of good information. So please read that, mark it up, ask Miss Heath or Miss Verona any questions you have. That's really good information to know for the test. Please know that information for the test. But what we're going to start with are the questions. So it's about on page 3 or 4 of your review. So on question 1. Question 1 states, what are the big differences between light and sound waves? We had like a little T-chart going on. That's really small, so we're going to make our own little T-chart over here. And we're going to have light rays over here, and we're going to have sound waves over here. So for light, we're going to use yellow. Woohoo! It's the sun. So for light rays, or light waves, main things about light. Light is part of the EM spectrum. That's a C. So the EM spectrum, or the electrical magnetic spectrum. So that's what type, it's electrical magnetic radiation. That's what type of waves it is. It's E&M, electrical and magnetism, because it's those two fields together that create light. Since that, because it's that, light does not need particles does not need particles to move, because it's part of the electromagnetic spectrum or electromagnetic radiation. It does not need particles to move. In fact, particles slow it down. Light wave moves the fastest through a vacuum, and it moves the slowest through solids. So fastest through vacuum, slowest through solids. And of course, anything in between, respectively. And because it's kind of more like when light moves, it's very independent, just pushing through. So if you're pushing through a solid, it's like you're in a really crowded hallway and you're trying to get to your physics test. And you're like, excuse me. You're having to push people out of the way. You're like, I'm not being late. Trying to get through. That's light, how light feels in a solid. In a vacuum, it's completely no one's around, you're walking across campus, you're enjoying your day all by yourself, moving as fast as you want. So speaking of speed, the speed of light in a vacuum is 3 times 10 to the 8th meters per second. I would know that if I were you. Okay, I would know that if I were you. That's very important. We're going to highlight this sucker. Very important. So that's how fast light speed is happening in a vacuum. And light waves are transverse waves. They're transverse waves, which mean that they are perpendicular to each other. Basically, if it's moving this way, so the movement is like left to right, its vibrations, so it's vibrating up and down. Vibrations, or up and down. It's moving left to right, vibrating up and down. So they're at a 90-degree angle, so they are perpendicular to, the vibrations are perpendicular to the motion. Anything else about light? Well, we're going to jump over to sound. If we have anything about light, we'll jump back. So sound. Sound are mechanical waves. Mechanical waves. That means that they need particles. They need particles. So they're kind of the exact opposite of light. They're the fastest. They're the fastest in solid, and they're the slowest in gas. And they don't even move in a vacuum. So they're fastest in solid, slowest in gas, and don't even move in a vacuum. So they're the exact opposite of light, and they're not independent. They're very needy people. They need people or particles around them. They're walking around going, yay, I'm in close quarters. And there's its speed. So the speed of sound in our gas, which is our atmosphere, is about 340 meters per second. And they are longitudinal. Longitudinally, I don't know, I can't spell. Longitudinal. Which, since they're longitudinal, that means they are parallel. So again, if we have movement going this way, it's moving that way, that means that the vibrations are going left and right. Whoops, where'd it go? There we go. The vibrations are going left and right. So they're going perpendicular, or parallel, to the motion. Those are the big differences between light and sound. Big difference between light and sound. So number 2. Let's zoom in here. You are standing 20 centimeters in front of a plane mirror. So if you see plane mirror, think a flat mirror. So you have a plane mirror, and it says you are standing 20 centimeters from said plane mirror. How far is your image from the mirror, or your image distance? That is something really good to know. Image distance. That is your DI. This right here is your DO. DI and DO. And actually, if you want to get technical, it is lowercase. There we go. DI, DO. If you remember, for a plane mirror, everything is equal. So your on the image would be 20 centimeters. Because you sparkle. So this would be your image. This would be the object or the actual thing. And it's the same. So your DO equals your DI. Always. Always. For a plane mirror. And everything equals. So your HI equals your HO, your theta I equals your theta O. Everything is the same for a plane flat mirror. There we go. So what is the apparent distance between you and your image? So you're trying to figure out how far you, the object, and the image are from each other. So basically, you just have to add that up. So you just do DO plus DI, and your DO is 20, your DI is 20, so you get 40 centimeters as your answer. Oh, and this is your answer, technically that. There we go. Now, number 3, if an object is placed 13 centimeters in front of the lenses, which is producing an image of 18 centimeters from the lens on the opposite side, what is the magnitude of the focal length for the lens? So we're going to draw it out here. When in doubt, draw it out. So you can kind of see what's happening here. So we got that. We're going to do a horrible con. Let's try it again. We're going to There we go. And our focal point is over here. And so that is placed in front of the lens. So this is, the image is 18 from the lens. Oh, you're looking for your focal point. We don't know where our focal point is. Try that again. There we go. So our image says it's 13 centimeters, and our image is on the other side of 18. So it's a little bit further. Let's do a different color. It's a little bit further. 18 centimeters. It doesn't give us height or anything like that, so we don't even know if it's inverted or anything fancy. Since it is a convex, it will technically be convex lens, and it, oh yeah, so it will be upright. I was correct. There we go. Just a few things to remember. So for a lens, upright and inverted stay the same. No matter if you're dealing with lens or mirror. It's your real and virtual that flip. For a lens, this side is your real side, this side is your virtual side. Just to make sure you remember. So this right here is your convex lens. And don't forget that this right here would be your optical axis. So just a couple of things. See what's going on here. But it's asking for the math. So a couple of things says the object is placed 13 centimeters. So that becomes our DO. Says that the lenses produce an image 18 centimeters. So that becomes our DI. And it's asking for the focal length. So it's asking for our F. If we have our equation, which is 1 over F equals 1 over DO plus 1 over DI. And we're looking for F. Let me make sure there's a little bit more room here. More room to do math. There we go. Let's spread out in room there. And so we're looking for F, so that stays there. Our DO is 13. And our DI is 18. Now, you can't just add these up because they don't have a common denominator. If you remember how to add fractions, you need a common denominator. Need common denominator. But you have a calculator. So let's let the calculator do the hard work for us. You can plug it in just like this, just like that in your calculator. So when you grab your handy dandy calculator, push parentheses 1 divided by 13 in parentheses plus parentheses 1 divided by 18 in parentheses equals that. So 1 over F equals 0.132. But you're not done. Do not stop there, because we're not looking for 1 over F. We're looking for F. So this is your inverse. So you need to take the reciprocal. You need to flip it. So you need to flip. Please don't forget this. This is the number one thing people forget to do, is they need to flip. So basically, you're flipping this, and you'll be flipping this, because this is just like 1 over, or that over 1. So your F equals 1 over 0.132. Then you can just plug that in your calculator. So your F equals 1 divided by 0.132, and you get 7.58, rounding. centimeters. Right? Everything's in centimeters? Correct. Correct units. Yay, centimeters. There we go. So that would be your focal point. So your focal point would be somewhere about there. That's where your focal point would end up being. Yay! So number 4. What is this picture demonstrating? So if you remember from the ripple tank, we talked about how waves bend around different things. So it's bending around. It's bending around. So we zoom in here. Waves are bending around the barriers. Bending around the barriers. So anytime it's bend around barriers, it's called diffraction. It is called diffraction. And let me rewrite that now that it's not zoomed in. Another way to remember it kind of makes a D shaped there. So diffraction. Do. That was easy. Okay, so you and your buddies went to a fun house right before your wave and optics test. You all start testing each other on the different types of mirrors and if you could label what type of image is being produced. You are 5.5 feet, or because you keep your handy dandy meter stick, or you can sit there and convert in your head, you realize that you're 1.68 meters tall, because we don't like those English units. Grr. So this is extra information. I don't need that. This is good information. Too tall. You're standing 1.5 meters away from the convex mirror that has a focal point of 4.25 meters. So that's your height. So that would be your object height. That's how far you're standing away, so that would be your distance of your object. Focal point, that would be your focal length. So there's our givens. There's some different things it's asking for. So it's asking for us, where is the image going to be? So let's draw it out. So we have this, we have a convex mirror. So on a convex mirror, you know that your focal point is on this side of the object. You're standing, so your focal point is 4 points. So that means you're standing, so it's out there. So you're probably standing about there. Again, just for reference, remember this is your optical axis. It quits jumping around. So optical axis. This is your, I'll rewrite it instead of having that random line there. This is your focal point. This would be your convex mirror. And of course, this is your object. Because we're dealing with mirrors, this is your virtual side. Remember, it flips for mirrors. In lenses, it's opposite. This would be your real side. This stays the same. This is upright. And this would be inverted. There we go. So light rays. When we're dealing with a mirror, you're going to draw a straight line, and then you're going to do a diagonal going through the focal point. Diagonal going through the focal point. Now, this is going to be kind of hard to draw a straight line, I will admit. So, wish me luck. I didn't even start in the same spot. Dang it. And it's going to be, my pen is not doing a very good job. So something like that. And then you do a diagonal line through the focal point. Oh boy. Diagonal line through the focal point. It's not even touching. Diagonal line through the focal point. There we go. And the straight line. And straight. Come on. Put him. Oh, so remember the dotted lines are your sight lines. Those don't really exist. And so there we go. And your image would happen where the lines would cross. That's where your image would happen. So you have a little person chilling there. So that is your image. So a couple of things. So we have so it becomes virtual, because we're on the virtual side. The image is diminished, even it's not by much, but it's diminished. And the image is upright. Now, distance. So we can sit there and do the math of the distance. So our equation, again, would be 1 over f equals 1 over do plus 1 over di. Because what it's asking for is the distance of the image. And that is our di. So this is what we're looking for. We're looking for our di. Now we have our focal point. Our focal point is 4.25. I'm going to give you a hint. It's a negative because you're on the virtual side. Anytime your focal point is on the virtual side, your focal point becomes negative. So it'd be negative 4.25 equals your distance, which is 1.5 plus, and you're looking for your di. We need di by itself, so this is being added. So the opposite of add is subtract. What you do to one side, you gotta do to the other. So you have 1 over negative 4.25 minus 1 over 1.5 equals 1 over di. You can just plug that in your calculator. Make sure you put parentheses around that. So you can just plug that into your handy-dandy calculator, just like that. So if I have your handy-dandy calculator, do parentheses, 1 divided by negative 4.25, in parentheses, minus parentheses, 1 divided by 1.5, in parentheses, equals. And that gives you a negative 0.902 equals 1 over di. Now, you're not done yet because we're looking for di, not 1 over di. So what do you need to do? You need to flip it. 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 You flip it. So again, this is like it's 1 over. So flip this side. You flip this side. So you get 1 over negative 0.902 equals di. So plug that into your calculator. 1 divided by negative 0.902 equals, and you get a negative 1.11 for your di. Don't forget your units. That is in meters. So that becomes our image distance, which makes sense. So if this is 400, that is 4.25. You're still about 1.5. Yeah, he's closer than you, so about 1.1. And it is on the virtual side, so it's negative. So that makes sense. So now we're looking for height. So our equation for height is hi over ho equals negative di over do. So oops, I didn't mean to cross it out. I'm going to highlight. So what this is, height of the image. So that becomes our di. So our hi, height of the image, hi. That's what we're looking for. But we have our ho. Our ho is 1.68. So we're looking for hi. Our h is 1.68 equals, that negative is part of the formula. That's got to stay there. So you're going to get a negative times a negative 1.11 divided by your do, which is 1.5. 1.5. We need hi by itself. It's being divided. The opposite of divide is multiply. And what you do to one side, you gotta do to the other. So that cancels out, and so you get an hi equals. So you can just plug that straight in. So you can do negative, parentheses, negative 1.11. But if you know that a negative equals a positive, divided by 1.5 times 1.38, and that gives you a 1.24 meters. So let's see if that makes sense. So you're standing 1.68, and it said it's supposed to be diminished, and we said that it's 1.24. It diminished. Woohoo! Makes sense. And now we need the magnification. So the magnification, we can actually use our di over do, or we can use our hi over ho. Either one works. I don't necessarily like messing with negatives, so I think we're going to use our hi over ho. Our hi we just figured out, it's 1.24. Our ho was 1.68. We plug that into our handy dandy calculator, 1.24 divided by 0.68, and we get a 0.74. And it says it was supposed to be diminished, so that it diminished. We're good to go. Woohoo! So 16. Why would the Star Wars space scene be less exciting if the movies obeyed the laws of physics? The biggest thing, biggest thing, no sound in space. It's because space is a vacuum. So no sound in space. So no sound in a vacuum. That's why. Woohoo. 7. The 4.6 centimeter candle is positioned 34 centimeters away from a convex lens. Please describe the image produced if the focal point is at 17 centimeters. So again, let's draw it out. So we have our optical axis. It says convex lens. I don't like drawing these suckers. Nope. So that's our convex lens. It should be more in the center. Where's that? Get more in the center. There we go. Okay. And it says that the candle is 34 away, and it wants to know if our focal point is 17. So focal point is there. We're going to have our image somewhere over here. So again, let's label a couple of things. Remember, this is a lens, so this side is real, and this side is virtual. Again, this one's upright. This is inverted. This is your convex lens. And this is our optical axis. Of course, that is our focal point. So let's draw it out. So on a lens, same exact steps. You draw a straight line, horizontal straight line to the lens, and then a diagonal line through the focal point. Just our sight lines are now on the virtual side. And then we draw a straight diagonal line through the center. Pretend like the line is straight. It's hard to draw a straight line on the computer. There we go. So where they cross would be our image. So our image would end up there. There we go. Hot dog. So let's go through and answer. So is it on the real or virtual side? It is real. Is our image magnified, diminished, or same side? I would say it's magnified. Our image is upright or inverted? It is inverted. So now we get to do math again. Woohoo! So let's look at our givens. So it says that we have a 4.6 centimeter candle. So that's the height of the candle. So that is our HO. 34 centimeters away from the convex lens. So that becomes our DO. And it says that our focal point is 17 meters. So that becomes our F. And we're looking for our distance of the image. We are looking for our DI. Again, we're going to go back to our 1 over F equals 1 over DO plus 1 over DI equation. It says that our focal point is 17. Our distance is 34. And we're looking for our DI. We need DI by itself so we can subtract. And what we do to one side, we do to the other. So we get 1 over 17 minus 1 over 34 equal 1 over DI. Put parentheses around that, and that's how you can plug it into the handy dandy calculator. Parentheses, 1 divided by 17 in parentheses, minus parentheses, 1 divided by 34 in parentheses, enter. And it, whoops, come back to me. I don't want to write with a highlighter. There we go. So you get 0. I'm still writing with a highlighter. Hey, you, computer, think. Thank you. So 0.029 equals 1 over DI. Are we done? Hopefully you all shouted no at your computers very loudly, scaring your parents, or guardians, or little sisters, or brothers. Big brothers. I don't know. Insert family member here. Maybe even your dog or your bird or your goat. Nah. So, no, it is not. It's because we got to flip it. Flip it. And so you get 1 over 0.029 equals your DI. You plug that into your handy dandy calculator. 1 divided by 0.029. And you get a 34.48 centimeters. So that is where your image is. So your image is actually really close. So your image distance is actually really close. So then let's figure out our height. So your height of the image, again, I'm trying to mark things out. I need to highlight. Come on. There we go. So the height of your image, so that would be your DO. So we have, or not DO, HO. So, man, my brain's not working. Let's try that again. Image, HI. That's what we're looking for. HI equals HO equal negative DI over DO. We're looking for HI. That's what we're looking for. So that just stays our HO, we figured out, was given up here. That's 4.6. The negative, that's part of the equation. It needs to stay. There we go. And our DO was just 34. We need that. It's being multiplied, or being divided. The opposite of divide is multiply. What we do to one side, we gotta do the other. So our HI ends up equaling, so we have 34.8 divided by 34 times 4.6 ends up equaling a negative 4.66 centimeters. That negative means it's inverted. Yep, it's inverted, and it is magnified. Wait, right? Do we say magnified? It is magnified, but not by much. So it could be magnified or same size. We'll make sure it obviously is, that you can tell the difference. We'll make sure on the test that you can tell the difference. So magnification, again, you can use your DI, negative DI over DO, or you can use your HI over HO. We used the D. Give us more room to work. Here we go. Okay. So we used the HI, the first one, so we're going to use the DI now. So a negative, your DI was 34.48. Your DO is 34. So your magnification negative, which means it's inverted. Look at your Candy Day calculator is 1.01. So it is magnified a tad bit, just a tad bit. So 8. A note has a frequency of 254 hertz. If the wavelength of the note is 0.845 meters, what is the speed of sound of that note? So on your calculations, hopefully you know that velocity equals wavelength times frequency. So we're given frequency, we're given wavelength, and we're looking for speed of sound. So this is F lambda, and we're looking for V. So not very much manipulating going over here. So 0.845 times 254. Plug that into your handy dandy calculator. 8 times 200, and you get 212.1 meters per second. Woohoo! There we go. So next question. What do humans and earthquakes have in common? You know what's kind of weird? What we have in common is the fact we both produce mechanical waves. We both produce mechanical waves. We both produce vibrations. So voices, so our voices, we produce vibrations. We vibrate our vocal cords so we can talk. And earthquakes, they vibrate the earth. So they both produce mechanical waves, both produce vibrations to function and do what we're supposed to do. Woohoo! So 10, how can you tell by looking at a wave which wave has the highest frequency? So if you're just looking at it, how do you know it has the highest frequency? The big thing is, so if we have, so let's look at different waves. So let's look at, we have that one. We'll look at that one. So which one would have the highest? So let's look at, so basically frequency, you count how many waves or how many pulses is actually happening. So we have 1, a 2, a 3, a 4, a 5, and this one's just producing 1, 2, 3. So you see how often the waves is being produced. So that's how you can tell which one has higher frequency. How often, like, is there more waves? And also you can look at the wavelength, you know? This wavelength is small, so small wavelength equals a big, can't spell big apparently, a big frequency. In this case, it is a big wavelength, which equals a small frequency. Remember, that is an inverse relationship. So what part of the electromagnetic spectrum travels fastest? Guess what? Trick question. Trick question. Trick question. Because they all move at same speed. They all move at the same speed. Remember what speed that is? Hopefully you all said 3 times 10 to the 8th meters per second. That's how fast they are. So they all move at the same speed because they're all light. They're all electromagnetic radiation. Same speed. Please don't miss that on the test. Okay, here we go. 12. Radio galaxies have twin radio jets and emanate from a center core. And basically an astronaut or an astronomer, thank you, finds a radio galaxy with a frequency of 30 megahertz. What wavelength of radio waves does the galaxy emit? So we've given us 30 megahertz. And don't forget the hint, you will need to convert. Dum, dum, dum. Don't forget the constant, your velocity, because it is a radio wave, so it is a light wave. So your velocity is 3 times 10 to the 8 meters per second. And it's an also constant that you need to know. Please know this. Know this. No. Okay, cool. You need to know that. And we're looking for your radio waves. So we have our velocity. We technically have our frequency, but our frequency we need to convert. So our frequency is 30 megahertz. So mega is times 10 to the 6th. So we have 30 times 10 to the 6th. Move over 1 just to, so we have 3 times 10 to the 7. Right? Yes. Hertz. So that becomes our frequency. And our equation is velocity equals wavelength times frequency. We're looking for wavelength. So we need wavelength by itself. So it's being multiplied. The opposite multiply is divide. So our wavelength equals velocity over frequency. Our velocity is 3 times 10 to the 8th. Our hertz is 3 times 10 to the 7th. You plug that into your calculator, and you make sure you put parentheses, and you can use the double E, don't forget about that. If you're using the double E, you don't have to put times 10. You can just do 3.0 double E, which is your second comma, and then your exponent. So your wavelength is just 10 meters. Woohoo! Very good. So what is the picture demonstrating? So we've talked about diffraction, that's light bending around a barrier. This is light bending in a medium, so it's refraction. Refraction. 14. What is the definition of index of refraction? So index of refraction is the measurement. It's your measurement of refraction. It's your measurement of refraction. So high index of refraction means thicker. So thicker material. Thicker material bends the light, or wave bends more. A lower end is thinner material. And the wave bends less. There we go. So if you shine a beam of light at a surface of a mirror, can you shine someone's eye? If so, what is this called? So the answer is yes, because again, come on. So we have a mirror, shine a beam of light, it will reflect, no, it will reflect. And remember, it reflects at the same angle. So it reflects at the same angle. It's object distance. So your object distance, so if the object is here, your object distance is the same. So everything is the same. Your DO equals your DI, your HO equals your HI, your theta O equals your theta I. Everything is the same. So there is a way to do it. You can sit there and bend the mirror, kind of do that with your iPhone or your watch. You can blind someone, not as well, not really blind, you can put light in their eye. And this is called reflection. So this is called reflection. 16. A tuning fork is struck, vibrating the fork and generates sound. What will happen if the tuning fork is put into water? We did this in our station lab. So when you put it in the water, the energy from the fork is transferred to the water, which causes the water to vibrate or splash. 17, last question. So we're going to use the diagram below. What is the speed, frequency, and period of our gamma ray? So speed, again, this is a trick question. Trick question. Because it should be 3 times 10 to the 8th meters per second, because that is the speed of light, because that is a constant. Please remember that. Maybe if I sing it, you'll remember. I don't know. 3 times 10 to the 8th meters per second. So frequency. So wanting to know what your frequency of gamma rays. So we're going to go over here. So gamma rays. So that tells us that our wavelength, so look at our little chart. So our wavelength is 10 to the negative 12. So that is our wavelength. And if this is our velocity, and we're looking for frequency, so velocity equals wavelength times frequency. We need frequency by itself. So our frequency just gives us velocity divided by wavelength. So 3 times 10 to the 8th divided by 10 to the negative 12. Again, you can use your double E divided by 10 negative 12. And you get your frequency to be 3 times 10 to the 19th. Make sure I plug that in right real quick. I forgot to put parentheses. For shame. Okay, yeah, that's right. Cool. So that is our frequency, and that's in hertz. Now, period. Period is just 1 over frequency. So our period would just be 1 over 3 times 10 to the 19th hertz. Wow. So again, you can just do 1 divided by your answer, and you get 3.33 times 10 to the negative 20 seconds. Ta-da! And we're done. So hopefully, if you have any questions, you'll come ask Miss Verona or Miss Heath. Hopefully this helped a lot. That's all I have for now. You will be given your equations. But you need to know what all the letters mean, the variables mean. I would know my units. Okie dokie. Have a wonderful day. Happy studying. Bye.